G'day chemistry students, and welcome to yet another video that's covering dot point 2.2.3. I believe this is the last one. It's on limiting reagent reactions. Slightly different set of calculations, still all revolving around the mole concept. Little bit of conceptual background first before we get into the calculation, but let's go. So a limiting reagent is the reactant in the equation which sort of stops the reaction from allowing to continue or move forward. And the best way to think about that is through a simple analogy like the one that I have here. So Khan Academy, again, brilliant with their analogies. If you're to make a hot dog, what you'll need is the hot dog or the sausage itself and the bun to make the hot dog in the bun, the thing that you actually eat. If you don't have the exact same number of hot dogs or sausages and buns, then you're not going to be able to make the maximum amount of hot dogs at the end. So in this instance, we have one more sausage than we do buns. So at the end, we end up with 4 hot dogs and 1 leftover hot dog. The limiting reagent is the thing that stops the process or the formation of hot dogs right in its tracks. Once we've used up all of those buns, no more hot dogs can be made. So what you end up having is a theoretical yield, the maximum amount of stuff that you can make. And then we also have an excess reagent, which is the stuff left over at the end, which didn't form into anything. Now, same idea can be applied to a chemical reaction. Main concept, a chemical reaction will stop if one of the reactants is completely consumed. So if you have 2 reagents at the beginning and one of them gets completely used up, then anything that's left over of that other reagent that has excess just won't be able to be used. It's not useful at all. And we don't consider it in any form of calculations. There are a bunch of different things and numerical, quantitative things that you can use in a limiting reagent situation, and a few different calculations that you can do, all of which I will show you in the next section. All right, so for this limiting reagents question, we have the following reaction to be looking at. So the following reaction occurred when 7.00 grams of sodium chloride, NaCl, and 95.0 grams of silver nitrate, AgNO3, were combined. So we have our sodium chloride, our silver nitrate, and we are forming silver chloride, sodium nitrate. Now, the first question that we're looking at to begin with is which reactant is the limiting reagent? So deciding whether or not we have a short supply of sodium chloride or a short supply of silver nitrate. The following question is how many grams of silver chloride were produced? So knowing how much actually reacted together, or how many moles of stuff reacted together, we can then determine how many moles of silver chloride was produced and find out the mass that was made. And we can also calculate how many grams of excess reactant remained. So if we can figure out how many moles of whatever the excess was, sodium chloride or silver nitrate, if we can figure out how much was left over, then we can also convert that into grams as well. So you'll notice that for these grams calculations or anything where we're using grams, we're going to be using moles as our way of comparing any of our substances and comparing how much they reacted compared to one another, or how much was produced at the end, etc. The number of grams, I guess, is a measurement that we can do physically, but when we're actually comparing parts of the reaction, the thing that we care more about is the number of moles that participated or didn't participate in a reaction. And you'll see that the entire way through when I start calculating. So first off, which reactant is the limiting reagent? Now, the only way that we can determine that is to find the number of moles of sodium chloride and the number of moles of AgNO3, which is our silver nitrate, which actually were present to begin with. So number of moles of sodium chloride present, will mass over molar mass is our formula. The mass of sodium chloride at the beginning is 7.00 grams, and the molar mass is the mass of the sodium. I'm just pulling up my periodic table. The molar mass of the sodium, which is 22.99 grams per mole, plus the molar mass of the chlorine, which is 35.45 grams per mole. And let's calculate that really quickly. So here I have 7 all over 22.99 plus 35.45. The answer for that is that we have 0.120 moles of substance reacting. For the silver nitrate, again, formula that we're using is M over MM. The mass that we have at the beginning, we can see that we have 95 grams reacting to begin with. And that's being divided by the molar mass of the silver nitrate. So first off, the molar mass of silver is 107.9 grams per mole, plus the molar mass of the single nitrogen, which is 14.01. And we're going to add on top of that 3 times the molar mass of oxygen, which hopefully we're starting to remember already is just 16, considering we use it so much. So to put that into a calculation, we have 95 divided by 107.9, oh, that's a 6.9, plus 41.01, plus, and I'm going to put all this in brackets, 3 times 16. The number that we get is larger than the other. It is 0.559 moles. So 0.559 moles. Now that we can compare the number of moles that we reacted, what we can see is there's significantly more silver nitrate particles that are reacting or present to react compared to the sodium chloride. What we can also see is that we need 1 sodium chloride for every 1 silver nitrate, so we need exactly the same number of particles to react with each other. What this means is that there will be an excess of silver nitrate, and this will be the limiting reagent. And while we're here and thinking about how much more silver nitrate we'll have at the end, we'll actually calculate that now. So excess moles of silver nitrate. Now that's going to be equal to the amount of silver nitrate that we have in total, so 0.559 moles. And we're going to subtract the number of moles of silver nitrate that will react with the sodium chloride. So they exist in this 1-to-1 ratio, which means it will have the same number of silver nitrate particles reacting with the sodium chloride particles, which means that 0.120 moles of silver nitrate will react with the sodium chloride. Everything that's left over is going to be excess. So 0.559 minus 0.120. The excess silver nitrate is going to be 0.439 moles. Now we'll need this for part C. I'll get back to that in a little bit. I thought I'd just do the calculation while I was talking about everything else. Let's just move everything down a little bit. The next question is, how many grams of silver chloride were produced? Now what we know is that sodium chloride reacts with silver nitrate and produces silver chloride, and we don't really need to worry about it, but I'll write it anyway. That doesn't really matter much for our calculations, but sodium nitrate also exists as well. And what you'll notice is, with this equation fully balanced, that the reaction exists in a 1-to-1-to-1-to-1 ratio, meaning that if I have 1 particle of sodium chloride, it will react with 1 particle of silver nitrate and produce 1 particle or 1 unit of silver chloride and 1 unit of sodium nitrate. Now, as I was saying particles, I kind of correct myself. I think that using the term unit would probably be more appropriate, considering that we're working with ionic compounds that have empirical formulas, but that's just a little bit of an aside, a little bit of a tidbit. Units would probably be more suitable to use as a term though. Now, if I start looking at this being in a 1-to-1 ratio, now what that means is if I have 0.120 moles of sodium chloride reacting with silver nitrate and it's in a 1-to-1 ratio, that means 0.120 moles of silver nitrate will react. And that's what we kind of already used here when we were doing this calculation over the side. But for silver chloride, what it will also mean is that there will be 0.10 moles of units produced at the end. Now, knowing this and using our what we call molar ratios or stoichiometry by looking at our balanced equation, what I can tell immediately is that the number of moles of AgCl is equal to 0.120 moles. And this is really important because from here I can calculate the mass of silver chloride, AgCl. Now at the moment it's unknown, but it's something that we can certainly calculate if we use our N equals M over M formula. Now with this in mind, again, all we'd have to do is rearrange our equation because we're calculating the mass of silver chloride here. That's what we're being asked to determine. And to rearrange the equation, that would be equal to the number of moles times the molar mass. We already know that the number of moles that will be produced is 0.120 moles, and that's going to be multiplied by the molar mass of the substance. Now I'm going to determine that by just putting it in the calculator. So, actually, no, I will put that in brackets and show the working first. That's how I've done it previously. So the molar mass we already know for silver is 107.9 grams per mole, and we also have to add on the chlorine, which is 35.45 grams per mole. And we can put all of that into our calculator. So 107.9 plus 35.45. The molar mass of silver chloride is 143.95 grams per mole. Now, if I multiply that by the number of moles that are going to be produced, the number of grams that are produced at the end is 17.202 grams. If we're working with our significant figures, I believe the lowest number of significant figures that we were given at the top, all the way up here, and I'll bring that down so I can show you. We were working with masses that had 3 significant figures, so that's what we're going to be reporting to down the bottom. That'll be 17.2 grams at the end. Part C is the last bit that we need to do. So the question was, just to remind you, how many grams of excess reactant remained? I'll show you the bit for part C. So we already determined that the excess number of moles of silver nitrate was going to be 0.439 moles. So the number of moles of excess, AgNO3, is equal to 0.439 moles. Now the mass of that excess is still unknown. We're about to calculate it, and we can do that by knowing the molar mass of the silver nitrate and the number of moles that are in excess. Again, rearranging our N equals M over MM equation to make the mass the subject. So here it's going to be equal to the number of moles times molar mass. That is going to be 0.439 times the molar mass of silver nitrate, which is 107.9. That's for the silver, plus the nitrogen, 14.01, plus the 3 oxygen, so 3 times 16. And that's all going to be put into brackets. Sort of running out of room a little bit here. Might adjust my camera a little bit. Sorry, just give me a sec. All right, so this last part here is starting to run out of room a little bit. What we have is 107.9 plus 14.01 plus, this is in brackets, 3 times 16, which is 169.91, and I'm going to multiply that by the number of moles that we actually have, 0.439 0.439. So the number of grams of silver nitrate that did not react that is in excess, and again, we're going to put this to 3 significant figures, 74.6 grams. And there we go. There are our calculations complete. Thank you very much, everyone. We'll do some more practice questions when we get into class, but I hope that gave you sort of a beginning conceptual understanding of how a limiting reagent calculation sort of works and what it looks like. Moving forward, we're going to be moving away from simple mole calculations and more looking at the idea of concentration. So the amount of particles, the amount of stuff that you can shove into a volume of liquid. There'll be lots of stuff to look at in that section, and this is probably the nuts and bolts of this topic. It sort of builds on what we've already looked at so far and brings concentration into the mix and is really important for all of the topics to come and all of the modules that we cover right up until your HSC exam. But until then, have a good one.